This video is meant for Mrs. Rose's AB Calculus class, and today our topic is the Fundamental Theorem of Calculus, Part 2. So we're going to start out with an example, and the first thing we're going to do is go ahead and take the antiderivative of this. So if we have our f of x equal, capital F of x equal to 1/2 t squared plus 2t, and then we just write our limits of integration like we would for any definite integral problem. And just like any definite integral problem, we're going to plug in our limits of integration. First, the big number. So this is going to be 1/2 x squared plus 2x minus 1/2 plus 2. So what we really get is that f of x equals 1/2 x squared plus 2x minus 5/2. Now they want us to find f prime of x, so all we're going to do is take the derivative of our capital F of x. So here we go. This is just going to be x plus 2. Do you notice anything? Perhaps possibly that x plus 2 is pretty much the same thing as t plus 2? Well, it should be, because the second fundamental theorem of calculus says that if f is continuous on an open interval containing x equals a, then for every x in the interval, if we take the derivative of the integral of a function of t, then it's just going to be that function but with x. So we can do this for pretty much any function. When we go to take the antiderivative, this is going to be just the integral from 4 to x of t to the 1/2 dx. So this antiderivative is going to be t to the 3/2, 2/3 in front, evaluated from x to 4, or 4 to x. So our f of x, so this is part A, f of x equals 2/3 x to the 3/2 minus 2/3 times 4 to the 3/2. When you do that evaluation, you're going to get 2/3 x to the 3/2 minus 16/3. So to demonstrate the second fundamental theorem of calculus, all we're going to do is take the derivative of our capital F of x, and of course that's going to be x to the 1/2, which is the same thing as the square root of x, and in fact it's basically this function but with x. Okay. So this function, when you have something other than just an x at the top, we have to do something special. We have to rewrite the integral in terms of just a variable like x, but instead of just using x, we already have x squared, it's going to be u. U equals x squared. So if we write f of u equals the integral from 5 to u of the same function dx, now we can use a chain rule of derivatives to take the integral. So we already know that when you take the derivative of a chain rule problem, you can do f prime of u of x times u prime of x. And if u prime of x is 2u, if u is x squared, and if u is x squared, then the derivative of u is going to be 2x. So when we go to do our integral, that whole derivative that we had before is going to be the integral of 1 plus u squared, just changing the u and the t, and then multiplying by u prime of x. Now we're going to plug in what u and u prime are. So plug in the x squared here, 2x here, and we're going to get 1 plus x to the 4th times 2x. So in general, when you're trying to differentiate definite integrals, when the upper limit is a function, where you have f of x equals some number down at the bottom, and then u of x, whatever function that is, times an integral of f of t, then the derivative is going to be that same function, replacing the limit of integration function inside, and multiplying by the derivative of the function from the top. Okay, let's try another one. We're going to make the top function here, that square root of x, equal to u. And I also wrote out the derivative of u. So we know that f prime of x is going to equal the cosine of the square root of x squared, because we plugged in what this function was in for t, times the derivative. So clean that up a little bit, we get the cosine of x over 2 square roots of x. Now this one's a little bit harder. We have two variable limits, so we need to have a split integral. So I'm going to split it into the integral from 0 to x of sine of t squared plus the integral of 0 to 2x of sine of t squared. Also, to make it a little bit more like the other examples that we've been doing, I'm going to change my limits to be 0 to x, and when you change your limits of integration, you have to put in a negative sign. So now I'm going to take the derivative slash integral and I really should put f prime of x here. So we have negative sine of, and you plug in your original function here, x, and we're squaring it, and then we multiply by the derivative of x plus sine of 2x squared times the derivative of 2x. And the final answer is negative sine of x squared plus 2 sine of 4x squared. And there's our particle motion problem from class, and that is it. Have a wonderful day.